So in this video, there's one more connection that I'd like to make between linear momentum and angular momentum, and that has to do with connecting the sort of differential equation statements about conservation with integral statements about conservation. So to sort of highlight what I mean by that, you recall that when in Module 2, when we were talking about conservation of linear momentum, one way to talk about conservation of linear momentum is to say that linear momentum can change due to forces acting on the system, right? And it also could change by mass actually carrying momentum out of the system, right? So plus the change in the rate of change due to mass flow. Right? So that was sort of the differential form of saying that linear momentum is conserved. The integral form of saying that linear momentum was conserved was this sort of before and after framing, where if you imagine there being some event that maybe applies some forces to the system, that the change in momentum from before the event until after the event, right? So in other words, the momentum final minus the initial momentum, right, is equal to the integral of the sum of forces that are acting on the object during the event. Right? And we labeled this idea, this quantity, the integral of the force acting on it, as the impulse. Right? So it's simply the statement that's equivalent to this one, but it's an integral formulation instead of a differential formulation. Depending on the situation, if you want to find how things evolve in time, right, having the differential equation is pretty useful. If you want to use a sort of before and after framing, where you're just basically interested in what things look like before the event and what things look like after the event, the integral formulation is more useful. Well, the same idea, pretty obviously applies to angular momentum as well. That is to say, we can write a differential form of angular momentum conservation. The time rate of change of angular momentum is the sum of the torques acting on the system, and you could actually have an additional term that would be the change due to masses that carry angular momentum. Right? So, and by analogy, you could also write an integral form. You could say the change in angular momentum was the final angular momentum of the system minus the initial angular momentum of the system, and that would be equal to the integral of the torques acting on the system during the event. Right? Which we would in turn could call the angular impulse. So all the sorts of ideas that we used in talking about linear momentum, the sort of idea of impulse, the idea of thinking about the amount at the end has to be the same as the amount at the beginning unless there's some external interaction or mass flow that causes the momentum to change. All those same ideas can be ported directly to talking about angular momentum. And to get at that, I just want to give a couple of sort of simple examples, and there are a couple examples on the Module 3, Exercises 3 as well, that you'll get a chance to work through. So the first is this sort of very silly kind of hypothetical example. I'm going to talk about an astronaut, right? And the reason I'm going to talk about an astronaut is this is an astronaut who's just happily floating in space and has decided to throw a frisbee. So I guess this is an astronaut who has more joints in his arm than he ought to. But there's the frisbee. So before, the astronaut is standing there, floating in space. The velocity of the astronaut is 0. The astronaut is not rotating, right? The angular velocity of the astronaut is 0. And so the astronaut's momentum is 0, and the astronaut's angular momentum about the astronaut's center of mass is 0 as well, right? Now the astronaut throws the frisbee. What's going to happen? Well, when the astronaut throws the frisbee, we can first of all think about what the frisbee must look like, right? The frisbee, there's my astronaut. The astronaut has just thrown the frisbee. The frisbee is now flying through the air at some velocity. And not only is the frisbee flying through the air, but we know that the frisbee is rotating, right? And since given how the astronaut would have thrown it, the frisbee is rotating clockwise, right? So if I think about what the frisbee's state is, the frisbee now has a momentum, which is the mass of the frisbee times the velocity of the frisbee. All right. The frisbee also has an angular momentum. It's actually going to have an angular momentum that's going to be pointing down. which will be the moment of inertia of the Frisbee about its center of mass times the angular velocity, which of course will be down. So this will be in the minus k hat direction. So what does that mean about the astronaut? Well, given that the linear momentum of the system was 0 initially, the final momentum of the system must be 0 initially as well, which means that the astronaut, first of all, must be moving backwards. And we can sort of say that that's got to satisfy the condition that the moment of the astronaut is minus, the final momentum of the astronaut is minus the final momentum of the Frisbee, right? So in other words, the momentum of the astronaut will be minus mass of the Frisbee times velocity of the astronaut final, right? Or in other words, the velocity of the astronaut final will be equal to the mass of the Frisbee over the mass of the astronaut times the velocity of the Frisbee with a negative sign. Right? So that's a statement of conservation of linear momentum, but we can also do the same thing with regard to the angular momentum. Right? Before there was no angular momentum, afterwards the Frisbee has a certain angular momentum, so it also must be the case that the astronaut has an angular momentum that's the opposite of the Frisbee's angular momentum. So the final angular momentum of the astronaut is the negative of the final angular momentum of the Frisbee. In other words, omega of the astronaut is equal to minus the moment of inertia of the Frisbee divided by the moment of inertia of the astronaut times the omega final of the Frisbee. All right, so you can see there's this direct analogy where the quantity is conserved. The quantity started out being, linear momentum started out being 0. Since there were no external interactions happening, the final momentum must be 0, so that means the astronaut must be moving backwards if the Frisbee is moving forward. Similarly, angular momentum was 0. Therefore, since there were no external torques applied, the final angular momentum must be 0. So therefore, if the Frisbee is spinning clockwise, the astronaut must be spinning counterclockwise. And of course, since the astronaut weighs more, his velocity is going to be lower. Since the astronaut also has a larger moment of inertia for rotation about the z-axis, his angular velocity will be lower as well. Okay. So that's one example of this sort of idea of conservation of angular momentum. And in the next video, we'll do one other example that has to do with a bouncing ball.